Hello everyone, I'm Veronica Irais Solis Tinoco from National Autonomous University of Mexico. It is an honor to be here and give a talk. The topic of my presentation is an optical sensor combining surface plasma resonance like extinction and near critical angle reflection for thin liquid field chemical sensing. This is the outline of my talk, and I'll start with a brief introduction with the basic concept of SPR and the objective of this work, and the description of our optical sensor configuration. Next, I'll describe the measuring principle and the mathematical model that supports the experiments performed with this optical sensor, and the materials and methods to perform the experiments, and finally, I present the results and conclusion. But what is a sensor? A sensor is a device that responds to some stimulus and generates a readable output. Exposure to a change in ambient conditions, for example, mass, refractive index, conductivity. The sensor alters one or more of these properties in a measurable manner, e- either directly or indirectly. Ideally, a sensor should be simple, low cost, and easy to use for the user. In this context, we can find a variety of sensors that allow the detection, identification, and dynamic studies in different fields such as biology or chemistry. In particular, optical sensors have attracted the attention of many researchers thanks to their versatile designs as well as to their facility to be miniaturized. They offer significant advantages such as low noise and immunity to electromagnetic interferences. Refractometric sensing devices belong to the optical sensor that include surface plasma resonance sensor (SPR). These sensors are thin field refractometers that measure changes in the refractive index occurring at the surface of a metal field supporting a surface plasma. Clever, clever SPR configuration have been proposed modifying or increasing their optical components, innovating the strategies for the intensity and phase modulation, as well as the methods for excitation and simultaneous detection that we know as multiplexing, all with the objective of improving the performance for sensitive of chemical and biological variables related to food quality, antibodies, and toxin and microorganisms, to name a few. In particular, the detection and quantification of microorganisms is of great importance in industrial fermentation processes, environment monitoring, and to address the global health challenge imposed by pathogenic bacteria. But what is SPR? SPR occurs on the software of nanometric structures with dimension less than the wavelength of the incident electromagnetic field. You can see in this figure when the electromagnetic wave interacted on the surface of the nanostructure with the electrons in the conduction band can produce localized, localized plasmon oscillation to generate surface charge density waves. The frequency at which these localized surface plasmas occurs are specific and correspond to those at which the electrons absorb the energy necessary to generate the collected oscillation. We can find different electric charge uh, distribution on the surface of the nanostructure called resonance modes. The number of the modes as well as uh, their resonant frequency and their width depend on the density of the electrons, size of the field, shape of the nanostructure, the dielectric function, and the external medium. Uh, Sharp SPRs at the interface of a thin gold film can be excited in internal reflection configuration using an optical prism, for example, Hertzsprung configuration. The characteristic spectrum of a SPR shows a clearer dip with its minimum uh, is easy to localize in frequency. The location and width of the tip is dependent on the angle of the incident and refractive index of the external medium, but only in the immediate vicinity of the interface. In many of the in many of the bioapplication of the SPR, the cold software modification generates very specific biosensor. But for the study of different strains, it's necessary a new binding molecule. Then, the main limitation of the SPR sensor developed to date is that they are sensitive to the external medium, only very close to the surface. So, we can foresee application in which it is important to sense physicochemical processes and chemical reaction near of the software, while simultaneously sensing the bulk of the external medium. Then we propose and study a device that combines SPR measurement with the capability of measuring the complex effective refractive index of the bulk of the sample. It consists of a semicircular prism with its flat base covered with the cold nanofilm in contact with a confined field of the liquid sample, as shown in this figure. The internal reflectivity at the glass color interface is measured with a laser beam and a photodetector as function of the angle of the incident. You can see in this video the cold nanofilm with 20 nanometers of thick that allows about the half of the incident light to go through it but still presents a SPR. The proposed device offers a level-free novel measuring tool to characterize different chemical solutions and biological suspension. The principle of operation of the proposed device is illustrated in this figure. It combines the plasmonic properties of a cold nanofilm and the sensitivity of the internal reflection configuration. We illuminate the system with a laser beam from an optical glass prism to a three-layer system consisting of the thin gold field in contact with a simple liquid layer backed with a glass cover slip. The external medium is air, and then the incident light excites sulfur plasmos bonds and the interface between the cold and the sample. However, the gold nanofield is thick enough to allow light transmission into the sample layer. In practice, we vary the angle of the incident at the class call interface from near normal incident up to crossing incidents to obtain the whole information given given by the reflectivity versus angle of the incident curve. We suppose that the refractive index of the sample N1 in general is a complex number that could correspond um, to the refractive index of a homogeneous absorbent solution or an effective refractive index of an inhomogeneous medium, such as a liquid suspension or small particles or biological cells. In this work, we developed a mathematical model of the reflectivity that could be fitted to experimental curves, allowing to infer the complex refractive index of the bulk of the examples and detecting the absorption of different molecules to the cold nanofield surface. You can see the mathematical formula for the for the reflectivity error. Then, to verify the principle of the operation of the proposed device and the mathematical model, a cold nanofield was fabricated. An optical setup was implemented and experimental measurements were performed using different biochemical solutions, and the mathematical model was fitted to the different reflectivity curves obtained. We select cold for the nanofields for its property to support sulfur plasmons and for its inert chemical nature and biocompatibility employed for biological applications. The schematic of experimental setup is shown in this figure. The setup consists of a semi-cylindrical prism fixed on top of two motorized goniometers. The rotation axes of both goniometers are aligned with each other, and the prism is placed so that the goniometers' rotation axes are tangent to and centered with the rectangular base of the prism. A laser beam is polarized choosing the P polarization, which is directed towards the center of the prism's base, as shown in this figure. We place the cold nanofield and its substrate in optical contact uh, with the flat rectangular face of the prism by matching the refractive index between the field substrate and the prism with an oil droplet of similar refractive index, 1.52. To confine a thin film or liquid example in contact with the cold nanofield, a clean cover slip is placed in front of the cold nanofield and inclined so that a microdoblet of the chemical solution can be deposited on the cover slip as shown in this figure. Then the cover slip is pressed against to the face on the cold nanofield forming a uniform microlayers. Then you can see in this video the experimental procedure to measure the optical information. Then here you can see the optical system and the measurement methodology. Then we prepared different chemical solutions to generate experimental curves of the internal optical reflectivity of the cold nanofield in contact with the microlayer of those solutions at room temperature. The sample liquids used in our experiment were distilled water as a reference, uh, fluorinated oil, using the microfluidics applications such as microdoblet technology, a disinfectant, sodium hypochlorite, and, an antibiotic solution of kenemycin monosulfate, a rich liquid culture medium used for ground bacteria, and a phosphate buffered saline solution used in biological research and cell culture application. We explored the possibility to determine the extinction coefficient due to polymer microparticles with a diameter of 1 micrometers and diluted in water. As a proof of concept for biofield sensing, we measured the optical reflectivity from a confined film of a suspension of live E. coli bacteria and PBS. The goal was to illustrate the potential of the optical device to detect the bacteria present and offer quantitative information about microorganisms suspended in complex chemical solution without biomarkers. Uh, Here you can see the experiment and theoretical fit curves of reflectivity are in this graph. To fit the model, we choose the report values of the refractive index of the prism glass, uh, the value of the bulk refractive index of gold and working wavelength of 550 nanometers, the refractive index for air was 1, and, and we adjusted the thickness of the cold nanofilm around its expected nominal values of 20 nanometers and obtained a bed speed with 17 nanometers. We assume the experimental thickness of 20 micrometers for the distilled water microlayer and a theoretical refractive index of 1.332. In this case, it's important to mention that the thickness has not much relevance in the theoretical model because of the refractive index of the water does not have an imaginary part. Then the two critical angles, 45 degree and 61 uh, degree, can be appreciated in the course. Also, the deep D in the reflectivity beyond the second critical angle is observed due to the SPR and the cold water interface. It can be noticed that the width of the SPR dip is quite wider than for an optimized SPR sensor. This is the price to pay for seeing the bulk of the sample liquid on the other side of the cold nanofield. The interval between both critical angles is highlighted in blue colored, whereas the around the that around the SPR from 70 degrees to 75 degrees is highlighted in green color. Um, Within the blue highlight interval of angles of incidence is where the highest sensitivity of the sample reflectivity is found, and where it might be possible to detect molecular absorption at the cold interface. So this zone should be used to infer the optical properties of the sample. As the theoretical model fits perfectly well within those intervals and angle of incidence, the distilled water curve has two important uses: fine-tuning the calibration on the angular scale and checking the applicability of the theoretical model to fit the experimental curves. Uh, Here, we present different measurements of the optical reflectivity for different samples to demonstrate the potential of the optical sensor. Here, you can see the experimental reflectivity of fluorinated oil, of sodium hypochlorite, of liquid culture medium, of phosphate buffer saline solution, and the antibiotic solution kinemasin. We can see that the curves have a similar shape with that of water. Also, we notice that in the figures, the theoretical 15 of the model, the black dashed line, coincides in shape and matches well with the experimental curves between the two critical angles. In table 1, you can see 6 refractive indices determined for experimental measurement with the 6 different solutions used in the example. These refractive indices were calculated using the theoretical curves fitting to the experimental reflectivity curve. In the graph, you can see the correlation between the changes in angular position of the reflectivity minimum with respect to the distilled water, and the changes in both refractive index determined by the critical angle method. for distilled water, for kinemizing, and the liquid culture medium. You can see a linear dependence. The refracted index sensitivity of the SPR angle shift is 168.35 degrees per RIU for our device. The previous chemical solutions are visible transparent, so the extinction coefficient is not necessary to describe them. However, when the example is absorbing or turbine, the reflectivity change. Curves change, and it can be used to measure the extinction coefficient as shown in this graph. In the graph, you can see the reflectivity curve obtained with a thin layer of polymer microparticle suspension in water and compare it with the corresponding curve for water. We can observe in the graph, the blue area, the extreme difference in height of the curves between the two critical angles. For water, the cyan curve, and for the polymer microparticle suspension, the green curve, indicating the scattering losses introduced by the microparticles in this case. Also, we can see that the theoretical curve, which is capable to reproduce the experimental data very well. Then, for polymer microparticle suspension, the extinction coefficient is 109.80 centimeters minus 1. This allows to conclude that the optical sensor and the mathematical model are capable of measuring the extinction coefficient of a non-homogeneous liquid sample. As a result, distinguish the solvent and the suspension particles in the liquid. Then you can see in the graph the reflectivity curve obtained for a thin film of E. coli bacteria, the orange curve, suspended in PBS, purple line. The fit of the theoretical model, the black dashes line, is also shown in this graph. Fitting the theoretical model required a considerable modification on the complex refractive index of the cold nanofilm due to the light scattering by the bacteria. Besides that, it is possible that some biomolecules of this complex solution were absorbed to the cold sample interface, interacting with the free electrons within the cold beam and changing its optical response at the operating wavelength. It is well known that the mere presence of some molecules on the surface modifies the optical response of the metals very close to the surface. But in this case, the cold is so thin that the most electrons are close to the surface. Also, the parameters used were 15.5 nanometers of the cold nanofield, sorry, and 20 micrometers of the live bacteria suspension, whose extinction coefficient is 4.85 centimeters per minute web. Sorry. You can see also a microscope image of fluorescence of the live bacteria E. coli in this slide. Then, as conclusions, we describe a novel level-free optical measuring configuration combining surface plasma resonance, near critical angle reflection, and light extinction measurements for thin liquid field sensing and characterization. We determine the sensitivity of the surface refractive index from 15 the SPR section of the reflectivity curve. Also, the device matches closely the sensitivity of the conventional SPR method while determining simultaneously the port refractive index and extinction coefficient. The presence of the live E. coli bacteria strongly modify the refractive index of the cold field, This could be a novel, fast, and level-free way of detecting the presence of live bacteria that could find application to monitor a wide range of microorganisms in environmental, clinical, and industrial examples. Then this is all, and thank you very much for your attention.